for the delay there. 4, 5, 4, 6 are combinations. Section 4.5, if you looked in your textbook, is just really short. It's just basically an introduction to combinations, and there's just one page in your textbook and then a few questions. So I've put these two together. So what we're looking at basically is how counting these combinations is different from counting permutations. So it says if 5 sprinters complete a race, how many different ways can the medals for first, second, and third place be awarded? So if you think of your spots, you have your first spot, your second place, and your third. So this is for first, second, third. So as they come in, there's 5 possible people that could go in first place. We have 4 possible people then for second, and 3 for third. So this is 60 ways. This kind of, relates to what we were doing with permutations in the other sections, where we had 5 objects and we were arranging them 3 at a time, if you want to think of it that way. 5p3 equals 60. So does our order matter here? Well, yes, it does, because we're talking about placement in a race. So order did matter. So this is an example of a permutation of 5 objects that are taken 3 at a time. So when the order matters as to a placement or positions or whatever you're talking about, then it's a permutation that you're working with. So in example 2 here, it says if 5 sprinters compete in a race and the fastest 3 qualify for the relay team, how many different relay teams can be formed? So it says visualize the 5 sprinters below. Since 3 will qualify for the relay team and 2 will not, consider the number of ways of arranging your 3 Ys and your 2 Nos. So we have, if we think of this as an arrangement, we have 3 people who are going to make it onto the relay team and 2 that are not. So we would have 5 ways of arranging those people, but we've got that repeat in there. So it's a 3 factorial divided by 2 factorial. So 5 factorial divided by 3 times 3 factorial times 2 factorial, well that's just 120 divided by 12, so that is equal to 10 ways. That shouldn't be in there. Does the order matter here? No, it doesn't. It doesn't matter. It doesn't say that you're going to put first, second, and third have to be in a certain order in there. It's just saying you're going to pick. You're going to choose the top 3 in order to win the race, or in order to go on the relay team. So does order matter here? Then no. So when order doesn't matter, then what you're looking at is a combination of objects. So this is an example of a combination of 5 objects that are taken 3 at a time. So our combination, our permutation when we were doing that calculation was a 5p3. Our combinations are with the C. So we had 5 objects and we're choosing them 3 at a time. So combinations is a grouping of objects where order does not matter. So we don't care what order you pick them in. We just choose them in, if you want to think of it that way. We just want you to choose them. I like to use the analogy of Chinese food. When you go to those combination places and decide on your meal, you can have 3 choices, 4 choices, or 6 choices. They don't care which 3 things you pick, and they don't care what order you pick them in. That's what a combination is. When it doesn't matter what order you pick these things in, you just need to pick them. So it says, for example, two objects, A and B, have one combination because AB is the same as BA. So if you think of that as Chinese food, whether you pick fried rice and lemon chicken or lemon chicken fried rice in that order, it doesn't matter. You're still going to get 2 items, and you're still going to get those same 2 items. The number of combinations from a set of n different objects where only R of them are used And each combination can be noted by NCR or N over R in a bracket, and there should only be one bracket there. Read N choose R. And is calculated by using the formula N factorial over R factorial times N minus R factorial. Oh, there's one thing missing here, where 0 is less than or equal to R is less than or equal to N. So your N has to be greater than 0, your R has to be greater than 0, and your R has to be smaller than your N. Example 1 says, a group of 7 people consists of 3 males and 4 females. How many different committees of 3 people can be formed from these 7 people? So it doesn't say that you have to pick Susie first, or the first person is going to be a certain thing, or the first person you pick has to be a male with black hair or anything like that. It's just saying make us up a committee. Okay, so our order doesn't matter that we pick them in. So if we take a look at this then, our N is 7. That's the number of objects we have. And our R in this case is a 3. We are picking them 3 at a time. So that means we're using our N choose R, or we have N factorial over N, sorry, I'm mixing my formula up here, R factorial over N minus R factorial. So this is going to be 7 choose 3. So 7 factorial over 3 factorial times 7 minus 3 factorial. So that's 7 factorial over 3 factorial times 4 factorial. So when you do your math on that, that's 35. So on your calculators, oops, got too many windows open here. I'm just seeing if my emulator's back up or not. No, I don't see it on here. Okay. I'll have it for your next one. So on your calculator then, you would enter in 7, then the math button. Whoops, I wrote that kind of small. And then that right arrow to get you to PRB. Then you choose 3, because that is your NCR button function. And then 3, because this is my N value, and this is my R value. And then equals. Okay, so B part says, how many different committees of 3 people can be formed if the first person selected serves as chairperson, the second person is treasurer, and the third person as secretary? So in this one, then, the order matters, because you have specific spots where you're putting them into. So this one is an order matters, so that means it's going to be a permutation. Oops, order matters. So that means we're going to use NPR. So that's N factorial over N minus R factorial. So in this case, it's going to equal 7 factorial over 7 minus 3 factorial, which is 7 factorial over 4 factorial, which is 210 or 10 different committees. Okay? So C, then, is how many different committees of 3 people can be formed with 1 male and 2 females. So it says, think you must choose 1 male out of a group of 3 and 2 females out of a group of 4. So again, it doesn't say you have to pick the boys first, then the girls, or girls, then boys. They don't care. They just want to make sure when you're done you have 1 male in the group and 2 females in that group of 3. So order doesn't matter. So that means we're going to do a combination. Okay, so if I'm going to choose one male out of my group of 3, then that means I'm going to do a 3 choose 1 combination. From my females, I'm going to do a 4 choose 2. I have the word and in there. From our last unit on set theory, I know the word and means I have to multiply these two things together. So what I'm doing then is 3 choose 1 times 4 choose 2. So that's the same as 3 factorial over 1 factorial times 3 minus 1 factorial. And then I'm multiplying that to 4 factorial over 2 factorial times 4 minus 2 factorial. So this is the same as 3 factorial over 2 factorial times 4 factorial over 2 factorial times 2 factorial. So this is 3 times 6. So we have 18 different committees for this one. D. How many different committees of 3 people can be formed with at least one male on the committee? Okay, so at least one means that you have to have 1, 2, or 3 males on this committee. So there's 2 ways that you can do this. One is using direct reasoning. Oh, that writing is a little bad. So in this situation, then we have cases. We have case 1, where we would have 1 male and 2 females. So that would be three choose 1 times 4, whoops, 4 choose 2. And that's what I had up there, so that would be 18. Case 2 is if I have 2 males and 1 female. So then that would be 3 choose 2 times 4 choose 1. So that's the same as saying 3 factorial over 2 factorial times 3 minus 2 factorial, and I'm multiplying that by 4 factorial over 1 factorial times 4 minus 1 factorial. So that's equal to 3 times 4, which is 12. My case 3 then is that I would have 3 males and 0 females. So in that case then I would have 3 choose 3 times 4 choose 0. So 3 choose 3, that's 3 factorial over 3 factorial times 3 minus 3 factorial times 4 factorial over 0 factorial times 4 minus 0 factorial. So 3 factorial over 3 factorial times, this 3 minus 3 factorial is just 0 factorial, so that's going to be a 1. So these will just cancel, so that leaves me with 1. 4 factorial over 0 factorial, which is just a 1. 4 minus 0 is 4 factorial, so I have 4 factorial over 4 factorial, so it's 1. So each one of these cases has a male on them, at least 3 males, so that means I could have 1 male or 2 males or 3 males. Or, if you remember from set theory, means I need to add. So I'm going to add my 1 male situation or case to my 2 male case to my 3 male case. So that means the number of committees I could have is equal to my 18 plus 12 plus 1, so that's 31 committees. So that's using the method of direct reasoning, where I do exactly what the question is saying, show every cases. Method 2 is indirect reasoning. Whoops. Oh, I don't know why I can't. So that's indirect reasoning. So in that way, what I look at is, okay, this one I broke it apart into each of the possible cases. In indirect reasoning, what I do is look at, okay, what is my total committee? What could that be? Well, my total committee is equal to that 7, choose 3, which I calculated before was 35. So the other way of looking at it then is to say, okay, what if I had no females on, or no males on there? That would mean that the most I would have is 3 females with 0 males. So you look at the direct opposite or the indirect of what the question asks. So this one says at least 1 male because there's 3. I'm going to do it where I've got number of committees with 3 female and 0 male. So that means I'm doing 4, choose 3. So I've got 4 female, I'm choosing all 3 of them, and I'm taking my 3 male and I'm choosing none of them. So that is equal to 4 factorial over 3 factorial times 4 minus 3 factorial times 3 factorial over 0 factorial times 3 minus 0 factorial. So I already know that that equals 1. So on this side, I have 4 factorial over 3 factorial times 4 minus 3. So 4 minus 3 is just 1. 1 factorial is 1. So 4 factorial over 3 factorial is just 4. So that means there are 4 different combinations of having a committee with all 3 females. So the number of committees with at least 1 male then is going to be what's left. So if I have 35 possible committees, minus 4 leaves me with 31 possible committees with at least 1 male. So there's 2 ways of doing it. When you take the total minus the total opposite of there, so where you'd have no males on there, or you can do each case by case. Either way is fine. So a couple of things to note, just basically a summary here. The formula of n choose r is the formula of npr divided by r factorial, right? That's the only difference between those 2 formulas. So dividing by that r factorial eliminates the counting of the same combination of r objects arranged in different orders. So it's taking out those cases where you have arranged those objects in a different order, because remember, we don't care what order they're in, so that's why we take it out. When solving problems involving combinations, it may also be necessary to use the fundamental counting principle. So for cases like the social insurance number 1, where they'll ask you what different combinations of numbers can you have, well, that's a choosing thing. You're choosing 10 out of 10 possible numbers. You're choosing 9 at a time, right? So you'll have your combinations that way. Where you put in restrictions is where you'll have different answers. So if there's no restrictions on it, then you have 10 choices, 10 choices, 10 choices, 10 for each spot. But sometimes combination problems can be solved using direct reasoning. This occurs when there are conditions involved. To do this, follow the steps below. So just like the problem we did. Consider only the cases that reflect the conditions. So our conditions were we wanted at least 3 males on the committee. Determine the number of combinations for each case, so that's what we did. And then we added the results. And we added because of that or in there. We could have had 3 males or 2 males or 1 male. Sometimes combination problems that have conditions can be solved using indirect reasoning. So that was the second method that I showed you there. And it says to do these, determine the number of combinations without any of those conditions that were in the problem. And then consider only the cases that do not meet the conditions. So that was having 0 males and all 3 females. Determine the number of combinations for each case identified in step 2, and then we multiply those results. We multiplied in determining the combination, and then once we found those results, we subtracted them from our non-case. So if you remember those few little things there, that'll help you immensely with solving combinations. So there's your questions to do.